Greetings, Saintsmen. We have lesson 10.1, segments and lines and segments that intersect circles. So there's going to be a little bit of vocabulary and terminology that we're going to discuss early on here. Make sure that for the entire chapter that you bring a compass and ruler or a protractor for every single class. All right, so that's going to be a critical part of this. So a few things. We have a circle here, right? How we identify this figure? Well, first of all, circles are not polygons, and we're not just going to call them a shape. It's going to be a figure we're going to refer to. Polygons, as you guys recall, are geometric figures. They're two-dimensional figures that are created by three or more three or more sides, right? And they'll have no side that's going to happen interior to it, right? So that all these angles will have nothing that's going to be exterior when we create every single vertex. So we're making a little triangle right here. So there's a minimum of three. One of the things is there's a number of things when you're learning the concept of a polygon when you're in middle school, and there's an issue with regard to being closed sides. Not so concerned about that notion. And we already have a previous definition to follow for polygon that's consistent. One of the things too is that the sides are quote unquote straight. And as you guys can see here, it's not so much that we don't have any straight sides. We don't have any sides, right? The entire thing is curved. And what we have here is this point that literally is called the center. I know, it's really revolutionary sort of idea that we have here. But this center is how we're going to define each circle. From that center to every point on the circle, okay? So every single point here that's on that curve is going to be on the circle. The distance from on the circle to the center is going to be the same, okay? So when we talk about this first of all, let's consider all the ways that we can put a line segment through a circle, okay? So first of all, let's take a look at this guy. We're going to create here. I've got a protractor here to give me a straight edge. This right here, which is what we know as mathematically a chord. Let me rewrite that word for you so it's a little bit clearer because my printing there was a little bad. This is what's known as a chord. So a chord, mathematically, is defined as a line segment geometrically ending, right? Because line segments terminate. They're two endpoints. With both of those endpoints on the circle, right? This, for example, right there, that's a point on the circle, okay? Now, let me get a little bit further into this now and draw another one of these, okay? And think about what I drew. I drew a line segment, and it goes through the center and has endpoints on the circle. Now, rather than reiterating that this particular type of line, which for the record is what's called a diameter, all right, it's the longest segment through a circle. Excuse me. That diameter, so we have that line segment, rather than referring to it again as always a line segment with both endpoints on the circle, which it is, right? This is a chord, but specifically this is a chord that goes where but through the center. So this kind of reminds us of the whole concept of like rectangles and squares, right? Where squares are a type of rectangle, but not all rectangles are squares, right? All the non-square rectangles are we just call it rectangle. Same thing with the diameter, right? A diameter is a chord, but not all chords are diameters. Diameter is a specific type of chord. Now, another way we could do this, right? We go line segment, we go terminates on the circle. We could terminates on the circle through the center, or we could also terminate at the center and on the circle. And specifically, this type of line segment is what's called a radius. All right. And again, let's describe it. It's a line segment. It's not a chord, right? So we have to describe it as a line segment. And let's describe its endpoints. One of them is on the circle. And the other's at the center. All right. So let's talk about how we define these things. Let's draw another circle. So get your compass out. My software just does it for me naturally, which is nice. I'm gonna have this point here, center. I'm gonna draw a few things here. Let's go ahead and get a diameter. Let's get another diameter. And then get oops. Chord. Another chord. Okay, let's gonna fatten up these points here, even though points technically don't have a size, but just to kind of help us out with kind of a poorly drawn diagram. Let's label these points that I have here. We have A, B, C, D, E, and F. Now I want you guys to think about this. How do we name polygons, right? We're going to name these as clockwise or counterclockwise as a collection of all the vertices. So I could start naming all these points that are on the circle, but I want you really to think about this. How many points are on a circle? Right? Isn't there going to be an infinite number of points? So, right, where there's a finite number of vertices, where you can think about, you can create an infinite number of points on the perimeter of a polygon, right? Like this guy. Oh, how about that? This pentagon, right? I could do an infinite number of points, but all the way around. But at those vertices, there's going to be exactly 5 vertices. I can't do the same for a circle. So simply put, do you know how we name a circle? I swear to you, it's just through that center. So this, and here's our notation. You just draw like a little tiny circle with a center in it, an E, and this is also what's known as circle E. Okay, so let's name all of the radii. Radii is plural for radius. The chords, every chord that's here, and all the diameters. So when we're shopping for our diameters, right, we're going to get that from the list of chords. Now all the radii. In other words, it's all the line segments that are from the center to a point on the circle, or on the circle to a point at the center. But I think it's easier if we start at the center, right? Because we could go to E to A, right? E to B, E to C. These are all line segments. I've got a little line segment on over the top. If you neglect to do so, it's not the end of the world. It's actually accepted. E, F, and that's it. We got our 4. All right. How about our chords? Well, we have AD, that line segment. We have AB. We have BF. And we have AC. We have 3 of them that include A, right? This point on the circle. Again, this is kind of poorly drawn over there, but that's okay. So the diameters. Now, in order for it to be a diameters are chords, right? So let's take a look. AD is a chord, but not a diameter, because AD does not go through the center. Neither does AB, but BF and AC both are defined as diameters. All right. Next up, let's not think about segments anymore. Let's think about lines. So, yet another circle you need to draw with your compass. So, here we go. Let's take this circle. Oh, that's not the center. Here we go. Let's find the center. That's going to be Y. And of course, you're gonna find your center very easily when you use your compass, right? You have the needle and the point. The needle that you're going to spin around, right? That you're going to rotate around using that instrument. That's going to sometimes dig into your paper. That's pretty simply put going to be the needle, right? Or going to be the center. So for circle Y, think about all the ways we can intersect this with a line. We have this line out here. It has no intersection and really no relationship. However, I could draw a line, and it's going to intersect. And it's actually easier. Let's do this one first. I'm going to do this guy, which is going to go through the circle and intersect at exactly 1, 2 points, right? So we could do it no way, no points, or we could do it at 2. At 2 points, this is what's referred to as a secant. This line is a secant mathematically. Simply put, a secant is just a line that intersects a circle and not just in any way, but specifically at 2 points. Next, we have 0 points. We have 2 points. Now, here's another way to do this, right? There's a way. And we might have to discuss this a little bit more in class. We're going to get infinitesimally close. And again, we have to imagine. I keep drawing this because I want to get a good version of this diagram. Now, this one very clearly intersects twice. So I'm going to go one more time here. There we go. There we go. That's a good way to do it. Okay. This is a line. Because theoretically speaking, these segments and these lines and these arcs and these curves are made of points, and these points have no shape or thickness. With that said, right, what we're going to say here, and this is what you're going to have to understand, because I kind of struggled this with a little bit in high school, because I kept on thinking about wheels. Like I thought about the wheel of my truck, like the tire of my truck, and that it's only really touching the earth at one place, which is true. Now you're thinking about, well, there's this, that's multiple places. It's kind of like a wide mark that it does it at. Well, there's a few things going on there. One, you have like that the tire is compressed, right? Because of the weight of it. But that circle ultimately has one location, one point that it is intersecting against that line. That line is what's referred to with regard to circles as a tangent line. So a secant line, and you have to think about this is not referring to triangles. We just learned about triangle tangents, right? But this is related. You're going to see why. All right? And if you can't already, right? A little preview for you to use your imagination before we get there. But a tangent intersects a circle, a tangent line. We have a line that does not intersect a circle. We have a line that intersects it at 2 points, which is called a secant. And then now we have a line that intersects a circle at 1 point. And that's called a tangent line. Moreover, this point right here is what's referred to as the point of tangency. All right. Let's think about how circles can intersect each other. Because now we've done circles and lines, but here we go. 2 circles. How many points of intersection? The 2, right? So, only way to do it, no matter how we overlap these, only way that it's going to be more is if we have circles of the same size and we coincide them. In other words, put one on top of the other, and then they completely intersect each other, and that's a whole different deal. It's like when we have lines that do that, right? We dealt with that algebraically before, right? When you guys had algebra 1, and if it's literally the line has the same exact equation, it's the same line, and it coincides. Now, let's think about how we're going to do this where we can intersect it in one place, okay? So here's one of them. So here's a circle, and then here's another circle. I'm going to show you. I'm going to like trying to get this guy, move him real close. Right, so there's like a point of tangency right there, right? And this is what we're going to call, it's going to be called a common tangent. Right, because the two circles have the same point of tangency, so they have that tangent, point of tangency in common. But I have to think about another way you could do this. Is it possible to intersect two circles, one not interior to the other? And it is. It would look like this, right? We're going to have a circle and another circle. And then I'm going to move this guy pretty close and boom. Intersecting again at that one common tangent. So again, here's your common tangent. Here and here. Okay? This would be 1 point x of intersection. And these are what are called tangent circles. Circles that do tangent things. Circles that have this tangency, right? That they're going to have just that singular point of intersection. Okay? All right. And of course, let's think about two circles, not a circle and a line, right? We already did circle and a line that don't intersect. But what are the ways that we could do circles that don't intersect at all? Well, here's one. Oops, that's not it. I like one shot, and I drew one that had a common tangent, right? A point of tangency. Boom. Doesn't intersect, right? Here's one that's actually pretty fun. Here's where they all share. Let's see if I can kind of like, there we go, alter this guy. Right here, these two circles share the same center. And these are what are called concentric circles. Okay? Concentric circles share con with in Spanish, right? Con center with the same center. So these are circles. These are, again, never going to intersect one interior to the other, but they're different than this initial thing, right? Oh, yikes. Probably need to draw a different color here. But the one on the figure on the left, where we have two circles, one interior to the other, but they don't share a center. There's one other way to do it, right? And again, it's going to have a circle here and just another circle right over here. One exterior to the other. This guy keeps making an ellipse. Just it's set on not doing. There we go. Goodness gracious. And this is our last scenario. So we had 2 points of intersection. There's only one way to do it. We have our 1 point of intersection, which we had 2 ways to do it. And then if we have no points of intersection, we have 3 ways to do it. So this is 0 points of intersection. All right. Let's take a look at a few more facts here about this, and then we're going to do 2 problems. 3 problems. I'm lying. 3 problems. Okay. Quite a bit to this lecture. A lot to discuss theoretically. So let's go ahead and create our circle. And then we're going to create a line of tangency. Here's our tangent line. Okay. This circle. as point P, the center. T. And this is line L. So the facts about this guy. This is, again, circle P, which is also known as circle, right? This is the notation. Rather than writing the whole word circle, you make a little circle and put a little dot in the middle, put a point in the middle. We have the point of tangency T. And tangent line L. Here's a fun fact. Gentlemen, here's where your minds are going to now start to go towards the same concept that we utilized just in the last chapter, because we dealt with trigonometry. And this term tangent should turn you on to the thoughts of trig, because it was a ratio in a specific type of triangle, right? So we have these laws of sine and cosine that apply to all triangles. Well, now we have this idea of tangency with circles, where we have here from the center to that point of tangency. This will create a right angle. So from the center to any point of tangency, it is a right angle. It is perpendicular. In other words, PT being perpendicular to line L. And that is going to be universal. More fun facts. Here's a fun one that has an immediate application to astronomy. I know so many amateur astronomers in our class. Astronomy, right? Stars, not astrology. The thing that I really encourage you to avoid. It's not very sound with regard to rational thought. Trying to create here this. You guys can see I'm struggling. Trying to go tangent to it's the touch screen. Trying to go tangent to the circle. So one point of intersection, and then to single point outside of it. Okay, that kind of worked. Goodness gracious. So I have P. And I have A, B, C. Okay, so here's what I know. B and C are points of tangency. Okay, when that's the case, watch. I have a right angle. Right angle. To this point right here, A. What will be true is that AB and AC will be congruent segments. All right? They have to be. You know why? Right angle. What do you know about PB and PC? What type of lines are they congruent? Absolutely, because they're both radii, and all radii are congruent, right? Because all circles, just like as you've demonstrated when you've constructed these over and over again today, you've probably drawn 8 circles from that center where the needle goes to every point on the circle is going to be equidistant. And then take a look here, right? I've created that hypotenuse right there. So when I create this hypotenuse, AP, it's going to be reflexively belong to both triangles. Now think about that, gentlemen. It's not ASS, that's hypotenuse leg, right? PC and PB a leg, AP a hypotenuse. Therefore, PCA and PBA are going to be congruent figures. They're going to be congruent triangles through hypotenuse leg, right? It's the exception to ASS. And then therefore, AB and AC have to be congruent because these are corresponding parts. Gentlemen, we just did a proof. So this isn't just made up. And because it looks like it, there is logical proof as to why this exists. Now, as we continue on, for every point outside of a circle, right here, right? For example, I'm going to call this point K. If I drew, right, two lines that are, there are exactly two lines that are going to be tangent lines to that circle, and both of those lines will be congruent. It exists for every circle. And as I just said, for astronomy, I want you to consider that for satellites. A satellite being some sort of object foreign to, right, something that's planetary, and it's going to orbit around it. All right. So something that's interesting there for you guys. Let's actually do some examples now with some numbers. The circle. All right. It's circle P. And here's the question. I'm going to draw some stuff here. See how this works. Make sure you guys connect these guys. I didn't do a very good job of that, but I'm just trying to complete these examples at this point. All right. I got P, I got S, I got T, and we got some distances here. This distance from here to here goodness gracious, this thing's killing me, is 51, PT is 24, and TS is 44. Gentlemen, question. Is TS tangent to circle P? How would it be? Well, you'd have to think about this. If TS is a tangent line, it would mean that a right angle exists right here. If there's a right angle there, then that would create a right triangle relationship between PT, TS, and PS. So the Pythagorean theorem would apply. So let's apply the Pythagorean converse. In other words, let's test to see if 24 squared plus 44 squared is equal to 51 squared. If it is, then this angle right here is a right angle. If that's a right angle, then TS has a tangent relationship to this entire circle, right? That's the only way it can exist as a tangent, is that we have to have that being perpendicular. Now, that's a lot easier done than said, right? Because I just gave a long-winded explanation, but just utilizing my deductive reasoning here. I'm not just making things up, okay? There's reasons why I do this, rather than it looks like it. So 24 squared is 576, according to my calculator. 44 squared is 1,936. And 51 squared is 2601. And I'm going to add these guys. And again, you guys can already see it in the ones place. This ain't going to work out, right? 2512 is not 2601, right? We were in the ballpark. It's pretty close. But no, this isn't tangent. I know, it's just one of those things, oh, it looks like it. Well, no, you actually have to test the dimensions and see if it works. Okay? Let's do another one. Got two more examples left here. Circle A. And I got some other stuff. Here we go. Okay, sweet. Jeez. All right, got B. Thanks. Here we go. B and C. And this is 24, and this is 36. And here's where I usually get some I get some interesting questions. So you guys are gonna have to think this one out, okay? But let me give you some information before we jump to anything. First of all, B is a line. I'm sorry, is a point of tangency. to circle A. Okay? Just a moment here. I gotta pull something up on Canvas. Please complete this problem. Okay. Find the radius. Here's where I usually get a kind of a foolish question. Mr. Granados, is 24 referring to just this segment or the entire segment AC? I mean, gentlemen, let's go over here. What is B, right? B, point of tangency, which means this radius, AB, is perpendicular to that tangent line, BC. If that's the case, this line AC has to be a hypotenuse. Has to be. Okay? The hypotenuse in a right triangle, make my 6 a little bit better there, in a right triangle has to be the longest side. So how on earth, how on God's green earth, could that 24 apply to the entire segment AC? Of course it only applies to this portion out here, okay? So you should be able to deduce that on your own. Now, we should be able to apply the Pythagorean theorem, right? AB plus BC. I'm sorry, AB squared plus BC squared is equal to AC squared. Okay? But here's what we don't know. We want to find the radius. That's this guy, AB, which is R, which is also this same segment right here, R. So when we go back through here, AB squared is really R squared plus BC. When we substitute in for what figures we have, or for whatever values we have for these segments, BC is really equal to 36 squared, and AC is equal to R plus 24 squared. Okay? Hope we're able to do this guy. You guys ready? R squared plus 36 squared is 1,296. And now we have R plus 24 squared. For the love of God, please do not do R plus 24 is R squared plus 1296 or 576, right? 24 squared, 576. It's not. This is R plus 24 times R plus 24. We have to FOIL here. R squared plus 1296 is equal to first R squared outer plus 24 squared, 24R, sorry, plus inner 24R plus 24 times 24, 24 squared is 576, right? So we have R squared plus 1296 is equal to R squared. Let's combine these R's, right? 48R plus 576, okay? Just doing some algebra, going back to algebra 1. Oh, I had to still do that? Yeah, of course. These are these things that keep coming up. And this whole thing about the quadratic, this already came up just recently, and we applied the quadratic formula. It was at the end of chapter 8. And some of you guys, you're like, oh yeah, he's going to say that, and it's going to, not come, and we'll have to deal with it again. Not true. So here's what's nice about this problem. Let's go ahead and get rid of these R squares, right? I'm going to subtract R squared, bring it over the other side. When I do that, I cancel both of them. So I'm left with 1296 is equal to 48R plus 576. And again, we're solving for R. We're solving for the radius. So let's get it by itself. So I'm going to subtract 576 from both sides. On the right, it's going to cancel. 1296 minus 576 is 720, which is equal to 48R. Divide both sides by 48. 48 factors out. And 720 divided by 48 is 15. So this is my radius. It's 15. All right. One last problem. It's actually, I think, a little bit simpler of an example than that last one, because there's no quadratic. We don't have to bring back foiling. But that's a little foreshadowing. You got to probably brush up on your foiling skills. See how those are doing these days. Let's take circle L here. Okay, and let's draw two tangent lines that are going to coincide at the same point. Okay. So this guy right here, I'm going to call this point J. This is H. And this is K. So, this out. JH is tangent to circle L at H. JK is tangent to circle L at K. I'm going to solve for X. How do we do that, Mr. Granados? Well, here are your values. HJ is equal to 7x minus 23, and JK is equal to 61. I think this problem's a lot more straightforward than the last one. You know why? Because remember, what did we learn back in this example up here? Way back here, right? When we have a circle, and we have a point exterior like A, right? Kind of like satellite to it, right? And then it's going to have exactly those two lines that are tangent to the circle that are congruent. So in other words, HJ is congruent to JK. Does this remind you, by the way, like the little circle, the little satellite thing? And then, do you guys remember that movie Independence Day with Will Smith? Right, and the whole thing with the spaceships, and they got to use the radio signals. They have to start bouncing them with several. Okay, I don't know. I'm just made a Will Smith reference. HJ congruent to JK. HJ 7x minus 23 means it's equal to 61, and then we're off to the races algebraically, right? Once it being a two-step equation, 76 is equal to 61 plus 23 is 84. When we divide by 7. Meaning that x is equal to 12. Gentlemen, that's what I got for you. First assignment is on Canvas. Good luck. And I will answer questions in class.